Everyone. Welcome to this next session in our MIPI Automotive series. My name's Ian Smith, the MIPI team here to moderate this session. So this is our fifth webinar in our series, navigating the complexity of in-vehicle network test and measurement to build a reliable MIPI A-PHY compliance program. Having read that, I thought we should perhaps should have given this session a slightly shorter title, but there we go. I think it says it all. I'm going to do a little bit of housekeeping before I hand over to Kevin. Firstly, you can download the slides from the Handouts tab on the right of your screen. As well as downloading the slide deck, you can also download a paper called Introduction to MAS, which is Introduction to MIPI Automotive SerDes Solutions. That paper gives you a kind of complete 360 on all the different activities inside MIPI that create and support the MIPI Automotive SerDes framework, of which obviously A-PHY is a key component, and the test and compliance programs are also key components of. In terms of timing, this session will aim to run for around 45 minutes. So we're going to have around a 30-minute presentation from Kevin, followed by around 10 to 15 minutes of Q&A. On the subject of Q&A, we'll take any questions you might have through the chat. So please type in your questions as Kevin goes through the presentation, and we'll answer those questions basically in the order that we receive them. So there's an incentive there to obviously get your question in early. Just to introduce our speakers today. So we've actually got Kevin Kirshner, Solution Architect at Keysight Technologies. And Kevin is a very active member of the A-PHY working group focused on test and compliance. And Kevin will be our main speaker today, delivering the presentation. But we'll also be very ably supported by Tom Kopf, who's COO of MIPI A-PHY. Again, a very active member of the A-PHY working group, focusing on the compliance or the development of the MIPI compliance program. And Tom will join us for the Q&A component later in this session. Okay, so without further ado, I'm going to hand over to Kevin to start his presentation.
Great, thank you, Ian. So let's go ahead and jump right in. So to frame up the discussion about the work being done for test and measurement of the A-PHY standard and the evolution of the compliance framework, it helps to take a look at where we stand in terms of the evolution of the in-vehicle network and the architecture that's driving these changes. So if we look at the edge of the network where the automotive SerDes exist, we have a very asymmetrical demand on the data throughput that drives from the edge toward the center. And in the center, we have maybe a more traditional symmetrical network where high power compute nodes and ECUs can exchange data. And as I say, a symmetrical communication network. So the asymmetry at the edge is driving high speed raw video data from camera sensors toward the center. And we're also driving high-speed video data towards displays at the edge of the network. So as these, let's say, frame rates, resolutions, and total sensor count aggregated on a single line increase the overall data rate on a given line, we see a corresponding signal integrity challenge that's presenting itself. And this is really driving, let's say, the need to think about how we approach test and measurement of the in-vehicle network in a new way. So we really see an advantage from, let's say, the OEM perspective in approaching the test and measurement in a standardized way here, so that we can evolve out of, let's say, a proprietary technology domain where single or sole providers source the technology to the OEMs. The OEM would prefer to see, let's say, an ecosystem where equivalent technologies can replace perhaps a supply chain constrained source, as we saw during the COVID-19 pandemic. So we'd really like to foster this ecosystem through a test and measurement program that ensures interoperability of these various components and it enables the OEM the freedom that they've been hoping for. So as we approach the electrical test of the SerDes link, it's kind of helpful to see where the responsibility lies within the kind of vertical organization of the automotive ecosystem. So, we have two endpoints and a passive interconnect here, and we have chip suppliers at either end who are supplying, let's say, the 5 transceiver. And then we have ECU or module suppliers who will integrate those transceivers onto a custom PCB layout that serves their application specific purpose. So the chip supplier in the end is responsible for supporting a link that goes from end to end. And this introduces the notion of, let's say, a port level interface, where instead of considering the performance of the PHY at the pin of the transceiver, we will treat it at the interface where the automotive header exists, right at the edge of the board. So the implementation includes the PCB layout, as well as any filtering, um, ESD protection, a common mode choke, or a bias T that it's used for a power over cable circuit. So um, this this kind of notion of a transceiver specification at the pin is not present in the automotive SerDes world that we see MIPI A-PHY contributing to. And this is, let's say, quite empowering for an ecosystem to standardize the test at a single interface, whether you're a chip supplier who would create, let's say, a reference MDI, or if you're the ECU or module supplier who's creating a custom implementation of that MDI. The OEM then can essentially evaluate silicon or modules at the same interface, sort of enabling that robust ecosystem of interoperable parts to be tested and swapped. So it's helpful to separate the test into 3 domains. We have transmitter electrical, receiver electrical, and then the passive interconnect or the link segment and harness test. So transmitter test is performed using real-time oscilloscopes with automation software that reflect the intention of the compliance test specification. And the receiver test, in a similar sense, is meant to evaluate the receiver robustness by using some type of injected noise interference on the line while evaluating the receiver's ability to receive symbols without error. And finally, we would use a vector network analyzer to evaluate the interconnect as well as the return loss of each endpoint of the SerDes link. So looking more closely at the transmitter electrical test, again recalling that the tests are defined at the automotive header interface, we essentially take a link and we break it into its 2 endpoints, and we would terminate each one into the oscilloscope in turn for their own transmitter valuation. So the test mode output of the device is controlled by either an I2C or SPI sideband. In fact, the hardware interface is not mandated, but typically we do see something like I2C for early silicon evaluation boards. However, because the intention of the A-PHY standard is to enable test and measurement even in end products, so modules that have minimized pin count and would not have an I2C access, for example, the specification has been provisioned so that the device can be placed into test mode in band using the data link. So if you connect the device with a link partner and then that link partner enables the test mode, the device can then be switched into the path of the oscilloscope and measured. So this allows us to do both early validation of silicon as well as validation of production level devices. And I highlight here 4 of the key measurements that we see and have been focusing on for the early test events inside of A-PHY. So we use the droop measurement as a way to monitor the RLC response of the bias T circuit. Essentially, we put a constraint on the filter response of the power over cable implementation in order to ensure predictability of the performance at the receiver. In a similar sense, the power spectral density measurement quantifies the power versus frequency, as the receiver implementation is very frequency dependent in terms of how linear equalizers or other filtering is implemented. We ensure the predictability of receiver performance by constraining the power spectral density of the transmitter output. One of the measurements that's really emerging quite a bit in many different standards, especially those that implement PAM4 and above, like A-PHY does, is transmitter linearity. So this is a signal to noise and distortion ratio measurement that's meant to quantify the nonlinear distortion in the transmitter. This is very useful because, of course, we have a channel which has well understood linear loss, and then we have receivers which are implementing linear correction techniques. So by bounding the nonlinear contribution of the transmitter, again, we enable a certain predictability in receiver performance by gauging that element of the transmitter. And then finally, jitter is also highly predictive of the receiver's ability to clock symbols because it would certainly affect the clock data recovery function of that receiving circuit. So here's an example of the A-PHY PAMX transmitter linearity measurement. And what I'm showing here is what I would say is, the most complex version of the measurement, where we're measuring the downlink transmitter linearity. So we inject an uplink disturbing signal, and that's what's represented here by a signal generator, which is injecting the uplink disturber onto the splitter. And then we have this hypothetical device under test that receives power over cable in the real application. In this case, the device terminates into an oscilloscope, so it doesn't have the power sourcing equipment on the link that it typically would in the real world. So we need to supply that DC power externally through a bias T. So we essentially get the signal through this long test channel into the oscilloscope. And on the scope, we run a piece of automation software that reflects the CTS requirements. So this software runs the tests, provides a margin analysis against the test limits that are set in the transceiver spec, and it can do this for all gears, and it can do it in both link directions, uplink and downlink. So the intention of a test suite like this is to be a comprehensive automated version of the CTS in a single user-friendly interface. And as accuracy of results is of course the ultimate goal here. We have to consider the impact that the test channel has on our measurement. And then the example I've used, we're kind of in a worst case scenario because we have a power splitter here that introduces 6 dB of loss. And then we have additional cabling elements, DC blocks, and the bias T, as well as this automotive adapter that goes from the header connector on the device to a 3.5 mm compatible connector. So we have significant loss. And as we, try to achieve interoperability and result correlation across test runs and across test equipment vendors, we really have to treat this with a de-embedding function. And for Keysight, we implement de-embedding inside of a tool called Infinisim, inside the real-time scope. And it's essentially a matrix math tool, which will take S parameters, and you can see there's a similarity here in how the diagram on the left looks, representing the measurement circuit, and how the user interface of the de-embedding tool looks. And that's not a coincidence. So we can essentially identify the measurement location and the intended point that we'd like to simulate the measurement location. And if we reference all of the S parameters for each individual block, we can essentially move the measurement location from where it actually exists, which is at the input of the oscilloscope, and move it all the way back to the left, right to the output of the device at the automotive connector. And if you remember, right when we started this talk, that's exactly where the reference plane is defined for this measurement. So once the Infinisim tool consumes the S parameters, it can generate an FIR filter, which we load into DSP. And as the data is sampled off the analog front end of the scope, it passes through DSP in real time. So we actually feed a transformed signal into the measurement and analysis engine inside the A-PHY automation tool. So as point of example here, I've de-embedded a channel from an A-PHY Gear 3 PAM4 signal. And if we look over to the far right-hand side here and we compare the peak-to-peak voltage of the raw signal to the de-embedded signal, you can see we recover that greater than 6 dB loss that we know is dominated by the splitter, but also has contributions from everything else in the path. We also see that de-embedding improves the symmetry in the eye opening in each of the PAM4 eyes. So, this is quantifiable and let's say even qualitatively just looking at it, an improved version of the signal. So this is a really key enabler for, let's say, an authorized test lab that might want to guarantee the absolute most accurate measurement possible. They can go ahead and do that by having well-characterized test channels with S parameters and de-embedding tools like the one I've shown here. So transmitter electrical test remains a very key element of the entire measurement program. And as I pointed out, it can be very predictive of how a receiver will perform, and therefore we've placed a large emphasis on it inside the A-PHY working group as the initial focus of our measurement correlation work. The reality of really all emerging high-speed technologies is that as we drive data rates higher and as we increase the modulation complexity from NRZ to PAM4 to PAM8 and 16, the implementation complexity of the transceiver really shifts from the transmitter to the receiver. So in the past, you know, decades ago, let's say, um, we could equalize the signal in the transmitter and effectively pre-compensate for the loss through the channel by doing a pre-emphasis or a de-emphasis in the transmitter. And by the time the signal would go through the channel, it would arrive at the receive pin with an open eye, and essentially all was well. Well, now, especially in an environment where we have a 15-meter channel length and highly attenuated signals, these are closed eye standards at the receive pin. So now we rely on the receiver to open the eye with linear equalization and other filtering techniques, as well as error correction and handling in the receiver. So there's just a great deal of complexity introduced in the receiver by trying to achieve, let's say, the application goal of a standard like A-PHY. So there's a corresponding focus on the test and measurement side that also has to shift from transmitter to receiver. And that's what we'll take a look at next. So the receiver test architecture for MIPI A-PHY is one that is performed on an active link. And this is maybe the first and most noticeable difference for those who are used to traditional bit error ratio testing. So in a system that's, let's say, not fully duplexed like A-PHY, PCI Express might be a good example. We have a dedicated transmit and receive path, and typically the device would have a functionality called loopback, where we can place a signal on its receive pin, and it will interpret it to its best ability and loop it and put it back on its own transmit pin. and we can connect a bit error ratio tester on the other end of that device, and the instrument can compare what was sent to what was received. So that's sort of a traditional bit error ratio measurement. Well, now we have a full duplex link where a single coax cable or a single twisted pair is responsible for both the transmit and the receive function. So both directions of traffic exist simultaneously. So that traditional notion of loopback test is no longer possible here. And keep in mind, we also have these somewhat sophisticated error correction and handling techniques. In A-PHY, we're talking about just-in-time noise cancelers and retransmission. So we need a real A-PHY port to act as a link partner to bring the device under test into the A-PHY link and to participate in a real exchange of data. And in the case of bit errors, to participate in retransmission. So this is somewhat of a fresh idea for how we approach receiver test. Um, in order to stress the device under test, which is ultimately our goal, to put it through the most stress that it will experience in the automobile and quantify its performance. So we send packets to it and inject noise onto the link. And the arbitrary waveform generator here is used as a programmable noise source, if you will, and it takes the noise profiles as defined in the MIPI specifications and turns them into digital record, and we output those as an analog signal, and it's coupled onto the link using a noise amplification and coupling fixture. If you look over on the link partner side, we place a worst case communication channel in between it and the device under test. That's so that we have a maximum insertion loss or a maximum return loss. Again, another maximum stress condition on the signal coming from the link partner going to the device under test. And finally, in the bottom portion of the image here, we have the test automation platform, which is responsible for making the CTS measurement. But in the case of receiver test, it's also responsible for directly accessing the device under test's register space, which is where the error counts are maintained. And it's also responsible for talking to the link partner and initiating the BIST test mode and sending the BIST packets. So briefly, the receiver automation platform is based on a piece of software for Keysight called the AE2010R. And just like the transmitter application that we looked at earlier, this really is the entity of, that contains the CTS. This is the tool that will translate what we wrote in the CTS into an automated test and produce the result that we compare to the limits set forth in the transceiver specification. It's also responsible for device control, and this required some work recently inside the working group to define how we can communicate with, let's say, an arbitrary device that we want to perform receiver test on in the A-PHY standard. And what we did was defined the command line interface, and this is, let's say, a minimum set of functionality required of the device. So you can think of this as very basic calls like reading specific registers that allow us to make the bit error ratio measurement. Now, because not every device will allow access to the A-PHY register space in the same way, this command line interface requires a custom DLL to be supplied by the device vendor, which essentially maps this very limited set of command line interface calls to a very specific access method for the device to get to the register space. So this was a very important step that we took in defining the receiver test method by including this command line interface in the CTS. We then make a hardware connection to the device under test, which is not mandated in the specification, but it can be, to the choice of the vendor, something like I2C. It can also be USB or Ethernet, but we make that hardware connection, and the custom DLL allows us to access the registers. So this is, let's say, a recent development in the CTS that's enabling our receiver test. So noise computation is another, let's say, key contribution of the solution, or let's say it's a requirement of any noise generator that we want to use for this test solution. So the specification spells out the various broadband and narrowband noise profiles, and then the test equipment vendor is responsible for turning those noise profiles into an actual digital memory that we can load into the AWG and output A-PHY compliant noise levels. And speaking of being compliant to the levels defined in the specification, it requires a calibration routine. And here, this is just an image of how we approach that. And it gives you a little insight into what the fixture we're using is actually doing. So the fixture has a 20 dB coupling path in it, and that sort of high attenuation coupling path is needed so that we can maintain the return loss of the through path between link partner and device under test. So all the while we need to maintain the A-PHY channel limits. We can't exceed return loss or insertion loss in our test setup by introducing new elements. So this 20 dB coupler seeks to do just that. But because it's such a high attenuation ratio, we actually have to amplify the noise coming from the AWG before it hits the coupler. And for that reason, we need to perform a calibration that is a function of the frequency of the noise being generated, because certainly the amplifier does not have a flat frequency response. So there's a frequency dependency on the amplitude output. So what we do is we place a load on the link partner side of the fixture, and then we place an oscilloscope at the noise amplitude calibration plane, and we can generate all the various frequencies of noise and calibrate their amplitude using automated routines inside the same test framework. So A-PHY has taken a leadership role in the automotive SerDes industry in terms of defining how a compliance program and ultimately a full interoperability program can be realized. And it starts, of course, with a transceiver and channel specification that's open for all implementers to access. And this is really in contrast, let's say, to the precedent set by proprietary standards, where these are closed, let's say, NDA restricted standards. So A-PHY is really blazing a new trail here because once we have such a specification, we can then define a compliance test specification, which is really a function of that transceiver spec. So the compliance test spec takes the transceiver limits and places them into something of a recipe for how to validate those critical limits inside the transceiver spec. And once we have a CTS, test equipment vendors like Keysight and MIPI can create methods of implementation. And this is yet even more specific implementation of the CTS. That's, a specific oscilloscope with a certain cable and fixture. And MOIs must be approved by the organization. So this is very critical because it requires measurement correlation events and a lot of hard work to make sure that the CTS is doing what it's intended to do. And finally, once you have an MOI, you can create a compliance program because authorized test labs can then take that MOI, replicate it in their lab, and use it to make certified compliance measurements for companies that want to make use of their services. So speaking of compliance programs, again, MIPI A-PHY is really leading the effort in this regard, and I think acting as an example, not just inside of MIPI, but to the automotive world in general, for how we can truly push forward into this ecosystem where interoperability is the outcome. And, of course, our primary goal here is guaranteeing consistency in results from run to run and from vendor to vendor. So it's been a focus right out of the gate that correlating test runs from one test equipment vendor to another in a very collaborative environment where we seek to let's say edit the CTS, really try to understand if we really have made the right assumptions in our initial implementation of the CTS. So this test ecosystem is built on this notion of transparency and collaboration. And in the end, as I hinted at, it ends in a flexibility for the OEM that's been desired for some time here. And it creates a competitive market where features can be delivered with cost optimization. You don't have to buy more than what you need, so to speak. Um, so this is sort of the goal of the compliance program, and here's how it's actually going. And I'd say it's been really a lot of fun for the last year and a half or so inside of A-PHY, going to these test events and participating first in the pilot, and then now we're well into phase 1 here, where we've done quite a bit of electrical transmitter testing, and we're starting to focus now on initial receiver test now that we have the test architecture so well defined. This phase also includes the formalization of the MOI, so gaining approval from MIPI leadership, documenting these things, and then moving into phase 2, where we formalize receiver and protocol testing, continually improve the process here. And as you see, as we move further and further to the right, we end up achieving the grander vision of the entire program as a whole. So as a brief snapshot of where we exist in the timeline of the compliance program for MIPI A-PHY, I want to point out that just this past December, we had the Test Fest in Hasselt, Belgium at Resilient Test Labs. So they've been a partner to us inside of MIPI as the host, both from a facility and from a test engineering standpoint, where we can occupy the space, run tests, and work with their own test engineers to get feedback for the feasibility of how our implementation will be broadly deployed in the future. Is it easy to use? Is it producing results in a way that we can correlate? So this is really an iterative feedback kind of a loop, and I think that this flow chart here from MIPI does a great job at illustrating that very fact. It shows that we have, as I hinted at earlier, that the transceiver specification feeding into a compliance test spec document, which then feeds into the generation of MOIs. And once we have MOIs, now we can sort of iterate in a loop and sort of improve the CTS and generate meaningful outcomes, meaningful test reports, and ultimately a full-on compliance certification program for the industry. So what we hope to achieve through the rest of 2024 is to add additional MIPI A-PHY device suppliers to this test and measurement event. And we do anticipate that will happen this year to get a second device supplier in the formalized measurement event. We also expect that the first receiver testing will be done in a formalized sense at one of these test fests this year as well. So it's really exciting. We've made a lot of progress in the last year and a half, and we know that we've got a lot of work still to do, but we're certainly ready to do it and looking forward to it. So with that, I'm at the end of my content, and I will hand it over now.
Yeah, thanks, Kevin. Thank you for your presentation. We can move to the Q&A component. Hopefully Tom will be able to join us. I think Tom has had perhaps an issue with his webcam, but I think Tom is able to join by audio.
Yes.
Yeah, hi Tom.
Yeah.
Thanks for joining. So yeah, well, there's one question in the chat. I'll put it up on the screen here. In fact, there may be two questions. I won't read it. It's quite lengthy. I'll just give Kevin and Tom a moment just to read through the question here and ask whether you can offer up a response.
Well, that's quite the question. Kudos to the person asking. Um, so, what nonlinearity figure of merit is being measured today? Um, can electrical TDEC-Q for wideband data be considered and measured similar to P2B data center compliance tests? So, the linearity measurement that we're using in A-PHY is a signal to noise and distortion ratio measurement. So, um, this is, let's say, something that should be familiar to IEEE standards. Multi-gig automotive Ethernet is an example of one that makes use of this SNDR measurement. Um, I'll say it's of the type that's being performed on PRBS 13Q style of pattern in A-PHY. It's not exactly that pattern. In fact, I believe there's sort of a positive polarity version of that pattern followed by a negative polarity version of that pattern. But in principle, it's the same style SNDR measurement that's being used in multi-gig automotive Ethernet with some provisions made specifically for the A-PHY standard. It's being performed only on PAMX signaling. As a point of reference here, the NRZ signaling is being analyzed with an IMASC measurement instead of the SNDR measurement. So I hope that gives a little bit of insight. It's a really great question, and yeah, maybe it merits a little more of an offline discussion.
Okay, thank you, Kevin. Okay, not seeing any more questions on the chat. So if you do have questions, please ask them at ASAP. I do have a couple of questions up my sleeve to give audience time to perhaps to think up their own questions. Kevin, Tom, so I mean, MIPI's historically has only really focused on conformance testing, producing CTSs for various specifications. But with A-PHY, obviously, there's a change with more focus now on compliance testing. Can you give any kind of history as to why that change has happened, and specifically why on A-PHY?
Yes, Ian, I think Kevin has raised it a little bit in the previous presentation. So there is quite a difference between how people are interacting in a standard mobile phone industry or something similar, and what kind of requirements there are from our automotive industry. While the cooperation between different companies and suppliers in a supply chain with a mobile phone is quite known. Let's say every OEM has their supply chain underneath. They have they're using standard components. They know what they're up for. A conformance was considered the best for the industry. There was no need in order to really come up with a compliance program. A compliance program does provide security and provides trust to a market, but in that case, it was not needed. The whole thing got quite changed with the requirements of the automotive industry, especially with what happened during the pandemic years, where automotive industry was lacking from suppliers giving them the semiconductors, and therefore also faced some huge losses in opportunities that they could not realize and ship to their customers. That drove the industry to a completely rethinking, saying that they need to have less customized solutions, but a broader variety in their supply chain in order to establish a more flexible situation as they had been having that before. In the end, MIPI came together and said, okay, what is needed in order to address that need? And we think that a compliance program is the perfect thing and tool in order to do that. The OEM and the first tiers no longer have to be experts in chips. They can go and specify their needs on a higher level without being able to say, okay, what is that chip capable of, and what is that chip not capable of, or that function, that camera. These things are being taken care of by that compliance program that we're building together. So people, in case that there is a shortage in supply, could look for a similar or almost identical product on the market and be assured that this can be dropped into their supply chain.
Thank you, Tom. I think it's a very clear answer. Kevin, anything to add?
No, I think Tom really hit that one on the head there.
Tom, just another question for you. Obviously, Kevin there at the end of his presentation mentioned the compliance program, gave a little overview of the current status. Is there anything you'd like to add on top of Kevin's words there with regard to that? I know you're specifically very focused on the compliance program itself. Anything to add?
Actually, not really. I could only underline what I've said before and what was said by Kevin. It's something that we are not doing on a rush. Maybe that's another angle that is worth to do. So we're taking our time. We're taking the needed thoroughness in order to really assure a compliance program that fits the market and has the transparency what is required. We prefer quality and discussion rather than having a rush on something which we need to revise later on.
And if anyone listening wanted to get involved, what would your advice be to them?
Well, if somebody wants to be involved in that, we're obviously happy to have any helping hand here, or anybody who is interested.
Oh, I think you've. Well, I don't know if we've lost Tom. I went on mute for a second, and I think he may have left us. Okay, no problem. Well, we'll move on. Kevin, obviously you spoke about the compliance test specifications for A-PHY. Who uses these specifications? Obviously, you mentioned certified test labs, but are they used elsewhere in the industry?
Yeah, absolutely, they sure are. So this is maybe one of the great elements of having a compliance test specification and having a method of implementation is that you can do so-called pre-compliance measurements in the lab. So if you're an implementer of a chip or a module, or if you're an OEM who's trying to evaluate these things, the fact that you can take a CTS and an MOI and replicate let's say, a formally approved test setup in your own lab, you can not only gauge whether or not it's time for you to go to a formal compliance event, but it gives you the ability to validate, characterize, and do some type of margin analysis of your device in the lab, on your own terms, so to speak. So before changes become incredibly costly with delayed design cycles, et cetera, having a formally approved test method is really empowering at the very earliest stages of development.
Okay, thank you, Kevin.
And worthwhile mentioning in that there is also debug functions in this whole test setup. So in case something is not ideal, the response, the softwares which are here used are usually in conducted in a way that they also give the developers a response on the overall performance on margins which are left over, and therefore also the ability to optimize their products before going to any kind of certification.
Okay, thank you, Tom. Okay, I note that we have reached time, and we need to wrap up our session today. Kevin, is there anything else you'd like just to add at the end of today's session?
I just want to thank everyone for joining us here, and to encourage them to reach out to us, really anybody inside the A-PHY working group, if you'd like to understand more about what we're doing or how to access these test tools and test methods. You know, it's something that we're very passionate about, and we're eager to partner with anybody who wants to do so. So, you know, please don't be shy, and we look forward to working with anybody who'd like to. So
Thank you,
thanks.
Kevin. And Tom, any last words from yourself? Well, you did drop off for a few seconds, but if you'd like to add anything, please do so.
That was also more or less what I wanted to say. First of all, thank you for listening in. And if there is any interest or any helping hand who would like to engage in the certification process here, program, please reach out to me. I'll be happy to chime you in.
Great. Thank you, Tom. Okay, well, thank you, speakers, today. Really appreciate your time and effort putting together the material and helping with the Q&A session. Just to reiterate, you know, there are plenty of ways to learn more. Key one, we've got the admin@mipi.org email address. If you do have questions, particularly if you're watching on demand and you'd like to ask a question, please fire it at that email address. We will get in touch with the right subject matter expert to get you a good response. Obviously, there are various resources on the MIPI website that you can find, like the MAS Introductory Guide to MAS, which gives an overview of all of our activities inside automotive. There's the MIPI blog, which contains lots of useful information, particularly related to new and updated specifications. If you want to stay up to date with specifically on automotive issues, we do have an automotive mailing list, which means you'll get just updates on MIPI's automotive activities and not all of the other things that we do. So please subscribe to that mailing list if that's of interest to you. And then just one last slide from me. This is session 5 of our 6-session webinar series for this week. Session 6 is coming up in around 30 minutes time. So time to go grab a coffee. Session 6 will come back and we'll have Intel talk about how they have taken A-PHY and ingested that into their automotive SoC architecture. So please come back in a few minutes and join us for the last session of this webinar series. Thank you very much for listening, and yeah, we'll see you again very soon.